In this video, I'm going to talk about a red-black tree. A red-black tree is an augmented binary search tree with the following attributes per node. So we have in a red-black tree, we would have value as in binary search tree. We will also have a pointer points to the left child and a pointer pointing to the right child. In addition to this, we also have two more attributes. One is color. The other one is parent. Parent is also a pointer, points to its parent. And color is 1 bit that indicates whether this node is colored or not colored. Conventionally, we use two colors, and one is red, the other one is black, and that's why it is called red-black tree. Red-black tree uses color as a mechanism to balance a binary search tree. So now in comparison with AVL tree, so this is a red-black tree. And for the AVL tree, it's also an augmented binary search tree, which has a value, a pointer to the left child, a pointer to the right child, and an integer that maintains the height of the subtree rooted at this node. So this is an integer. AVL tree uses the difference of heights between its own subtrees, which is called the balance factor, to balance a binary search tree. Now, in terms of storage, RB tree uses 3 pointers, and pointers is bytes. It's a memory address which is a byte addressable, so it's 8 bits. So which means that there are 3 pointers, and there are 24 bits, and plus one color bit. For the AVL tree, we get height. Height is an integer, so it could be 32 bits to represent a. And the left and right child, 16 bits. Hence, in terms of a storage, an AVL tree requires more space for the node than a red-black tree. A red-black tree must satisfy 5 properties. So each node is colored either red or black. So that is the first property for a red-black tree. And then the second property is that the root is always color black. And the third property is that for each leaf, it has an empty left link and an empty right link. So in other words, for the node that points to none or nil points to none, we will think of that as a special kind of node. We call it nil node. The nils are nodes, and they are colored black. Okay, so this is the third property. And the fourth property is that each red node must have two black children. And the last one, all paths from the root to new nodes or pass from the root to new nodes have the same number of black nodes. Any tree that can be colored this way is called a red-black tree. Now, if we have a red-black tree, why is it balanced? To see this, that TB and red-black tree of AND nodes and including new nodes, which we know are always colored black. Let H be the height of T. Okay, we want to show that H is the big O of log n, because this implies that T is balanced. At T prime B, T by removing all the red nodes, hence the black height is still the same. That is the black height, let's call it BH of T prime, is the same as that of T, as T. This is a red-black tree without red nodes, meaning that all the nodes are black, and they all have the same height, so you must have the following shade. The square black indicates new nodes. We also let n prime be a number of black nodes, which then we have n prime is less than or equal to n, because T prime is T by removing all the red nodes. We also know n prime is equal to the root 2 to the 0 plus the next level 2 to the 1 plus 2 to the BH. And for instance, the black height, which means the number of black nodes of this tree, is 4. The last level, or the bottom level, you have 8 nodes, so which is 2 to the 3, so which is equal to 2 to the BH minus 1 is equal to 2 to the BH minus 1. This indicates that the black height is equal to n prime plus 1 and log. And since n prime is less than or equal to n, this indicates that the black height is less than or equal to log n plus 1. And since h is at most 2 times BH, on each pass with only black nodes, you can insert red nodes in between. Actually, its h is strictly less than 2BH. This is equal to less than or equal to 2 times log n plus 1. Hence, we know h is big O of log n. This means that any red-black tree is balanced. Okay, so the next question is, how do we build a red-black tree? We can build a red-black tree using insertion. For any node to begin with, we always color it black. like this. And then we use binary search tree. So we use binary search tree insertion to insert a new node. And that new node will be colored red. So any node, let's call it of new node with value x. Just call it x. And you will find its location. For instance, it could be here. So this is x. And let's color this red. Insert this way. Okay, so this is a red black tree. Now let's say I have another node to insert, and let's say I have this node inserted under this red node. So this now is my new node X, and I have the number of blacks are the same, but this now I have two consecutive red nodes, which violates the property of red-black tree. Hence, we need to restore. In here, we're going to look at the following. This red node is the node that's inserted at the bottom. We call it new X. Then its parents could be a left child or a right child. Now let's focus on a left child parent. And the case where the parent is right child is symmetrical. And we first look at the easy case. In this case, we have a violation here. Okay, so this is the first violation starting from the bottom. So these boxes to indicate they have the same black heights. At the beginning, this A and B is just nulls, and this entire one, E, is a null. That's at the beginning, and EF is nulls. But gradually, this recoloring would move along the way up to the root. Hence, somewhere in the middle, we would end up like this situation. Remember, all these boxes indicate that the number of blacks are the same. For this case, we simply do a recoloring. What we do is recolor B and C from red to black, and then recolor A from black to red, and then we move X up. So here, then we can see, so this part has the same black height as before, and this part is a subtree satisfies red-black tree properties because all these boxes have the same black heights. But if the parent of A is red, then we have a violation. That means now it will come back to this situation. You got two consecutive reds, and then depending on whether A is a left child or the right child of its parent, then we are going to restore. We're going to recolor the nodes so that we will have all the properties of red-black trees satisfied. So this is the easier case. Now let's look at the second case. The second case, again, this new node is a right child of its parent. but its uncle, which means this node, is red. For case 1 and case 2, we just need to recolor those nodes. We recolor B and C to black and A to red. So this is similar to the previous situation. For this new tree, new subtree, they have the same black height as before, but the only concern here, its parent may be red. In that case, then two, there are two consecutive reds, and then going back to the position where we came from. And this A could either be the left trial or the right trial, which is the other symmetrical situation. For these two, then recoloring will go up until the root is reached. Now let's look at the following case. Here we have the new node as a right child of its parent, and we have two consecutive reds, and the uncle, the new node's uncle, which is this node, C, is black. Now to begin with, before this new node is inserted, it's red-black trees, which means all these boxes have the same black heights. Now we want to restore them. To do so, what we want to do here is we are going to move X up here. We're going to move X up here, and we're going to do a left rotation on X. So then E will move up into B's location. Then B will become the left child of E, and C becomes the right child of B. All these boxes have the same height. Okay, so that's what we do. But then we have two consecutive reds in one direction, in the same direction, the left and left. And then this is the same as the next case. Okay, so next case is this. So for this case, what we do is we're going to recolor B to black and A to red, and then we're going to do a right rotation on A. Hence B will become the root, and now remember B has been recolored to black, and A has been recolored to red, and that's what we end up with. Remember, all these boxes have the same black height, hence this tree now has the same black height as before insertion, and this is a red-black tree, and there is no need to propagate up. So we are done here. This means that during this process, we can see that once rotation begins, we only need at most 2 rotations to restore coloring, and the construction is done. The conflict has been resolved. Otherwise, if we only involve recoloring, then it may propagate up to the root. Now, once again, if a rotation begins, either one rotation or 2 rotations are what's needed, and then that's done. If we're recoloring, we recolor all the way up. If the root is red, then finally we just need to color it black. Then the entire tree now is red-black tree. As we can see, actually, I'll say red-black tree is even easier than AVL tree by just looking at their colors for doing insertion, and also it requires much less space to store one node. The drawback now is the height of the red black tree may be higher than an AVL tree. Next, we're going to see a Python implementation of insertion into a red black tree. For this, we would need to look at its parent because, as we mentioned earlier, we would want to know its parent and we want that to be done efficiently. So we augment what we said earlier. Now the node contains a value, contains a, let's call it color, parent, and then a link to the left child and a link to the right child. And it still saves space because parent is only a pointer, which is memory address. And memory address is bytes addressable, which is 8 bits, compared to storing an integer, which would take much more space than that. So that is for the node of a red black tree. Once we have a parent node, then the insertion will be efficient. And first, for any new node, we simply color it red. Then we use binary search tree insertion to insert that node into an existing tree. And if there is a conflict, which means that the new node's parent is also red, then we will look at whether this new node is a left child or the right child of its parent. And so then we can use what we just said to recolor and do some rotations necessary to resolve the conflicts of two consecutive reds. And the main part of it is this, which it's actually easier than doing AVLs, than maintaining balance in AVL. It's just you just need to know that a new node's parents and new node's parents' parent, or you can think of the new node's grandparent. And depending on which side, as we shown earlier, you can pretty easily to maintain the red-black tree properties. This is the end of this video. Thank you for watching.